Hi everyone, this is Mrs. G.A. and today we're going to do a quick introduction to our reciprocal trig function graphs. So as a quick warm-up, I'd like you guys to pause the video and sketch a graph for the parent functions of sine, cosine, and tangent. Alright, so here you can see our sine, cosine, and tangent graphs. So today when we're graphing our reciprocal functions, we're actually going to keep in mind what these parent functions look like. And we're actually going to use it to help us graph the reciprocal. All right, let's start with cosecant. So cosecant is the reciprocal of sine. So we know that any of the values from our sine graph, if we take the reciprocal of that value, that will be the value for our cosecant graph. So with sine, actually with all of our values, the values we really care about are when they cross the x-axis. So I'm going to start by just sketching with the dotted line our sine graph. Again, this is just a little guideline for us to look at like this. So since sine is the reciprocal of cosecant, we know that when sine is equal to 0, we know that cosecant will be undefined, right? Because the reciprocal of 0 is undefined, which means wherever we have an x-axis, that's where sine is 0, we're actually going to have a vertical asymptote for cosecant. So any place that I see an x-intercept, I'm actually going to sketch in a vertical asymptote. So cosecant has repeating asymptotes, just like tangent does. And you can see that it's actually going to occur, the asymptote occurs every half of a period. And then from here, well, we know that these values here are positive 1 and negative 1, and the reciprocal of 1 is 1. So that's going to be a value for our cosecant graph. The reciprocal of negative 1 is negative 1. So these values are exact. And then the way these graphs look is you actually kind of take each of those points and they kind of act like a vertex of a little mini parabola within each region created by your vertical asymptotes. So this is what our cosecant function looks like graphically. So just like our sine function has a period of 2 pi, our cosecant function also has a period of 2 pi because actually 2 of these little mini parabolas here and here constitutes a single period because we need both of them to start repeating the pattern. So our period for the parent function is 2 pi. And if we want to describe those repeating asymptotes, again, we name 1. Any asymptote that exists. So in this case, we could use 0, we could use pi. Again, sorry, we're scaling this by pi over 2. We could use pi, 2 pi. So I'll say let's pick pi, and then we say how often it repeats. So it repeats every pi units. Remember, it repeats twice every period, so every half a period. And then we say plus pi n, where n is any integer. So this would add any multiple of pi, which would therefore describe all of these repeating asymptotes infinitely. But again, we could name it in any way. We could say negative pi plus pi n. We could even say 0 plus pi n. So we could just say pi n, and that would describe every asymptote that exists. All right, now let's try our secant graph. So secant is the reciprocal of cosine. So again, we're going to kind of follow that same process that we did with our sine graph. I'm going to start by giving ourselves a little guideline here of our cosine graph. Something like this. So we can continue down a little more. And we are scaling this by pi over 2. And so remember, wherever cosine is equal to 0, so when cosine is equal to 0, its reciprocal secant will be undefined. And therefore we will have an asymptote. So just like our secant graph, or our cosecant graph, our secant graph has repeating asymptotes, except these occur whenever cosine has an x-intercept. So whenever cosine is 0, we have our vertical asymptote. And then we can take the reciprocal of some of the nice easy points like +1 and -1. That will be the same point for both our cosecant and, or our secant and our cosine graph. And then it makes that same shape that our cosecant graph makes. So those values at the top and bottom of cosine become kind of like a vertex of our little mini parabolas. So there's our general shape. The period of secant is 2 pi, same as the period of cosine. And again, we can describe those repeating asymptotes by naming any asymptote that exists, like pi/2, and then describing how often it repeats. So it'll repeat every multiple of pi, so we can say plus pi n. All right, and then last, let's talk about cotangent. So cotangent is the reciprocal of tangent. So we can kind of, I'll sketch in a quick little graph. Let's scale this by pi/4. So we know that our tangent graph looks something like this. And then we would have an asymptote, a vertical asymptote at pi/2. And then we start the same pattern again. Looks like this. I'm not going to sketch in the asymptotes, although they are going to be important for us when we're graphing here. So for cotangent, since it's the reciprocal, we know that when tangent is equal to 0, cotangent will be undefined, meaning we will have a vertical asymptote. So we have a vertical asymptote at -pi, 0, pi, and that would repeat infinitely. But there's something else we know. We know that when tangent is undefined, so wherever there was a vertical asymptote for tangent, well, the reciprocal of undefined is actually 0. So cotangent will equal 0. So wherever we had a vertical asymptote previously, that will be an x-intercept for our cotangent graph. And then we do have those reciprocal values. So like this value of -1 will be the same for cotangent, and this value of +1, the reciprocal of 1 is 1. So you can see that it's actually going to look very similar to our cotangent graph, but it's actually going to be decreasing within each period. So it looks like our tangent graph, but reflected vertically. So again, we could take a few more of those points. So we know this point pi/4, 1, the reciprocal of 1 is 1, and here the reciprocal of -1 is -1. So those points are shared. And our graph looks like this. And then, of course, that will repeat in each period like this. And there you go. So we know that the period, we can see that our period is the same as the period of tangent, so it's pi. And then we can describe our asymptotes same way that we have done for secant and cosecant. Name any asymptote and how often it repeats. So I see there's one at 0, and I see it repeats every pi unit. So it just repeats once per period. So we could just say pi n equals x equals pi n. Let me add that in the front. X equals pi n, or we could say x equals pi plus pi n, or -pi plus pi n. Remember, any asymptote that exists, and then how often it repeats. So again, for our reciprocal functions, you can really use your other, like the corresponding reciprocal function as a guideline. And just remember 2 key things. The reciprocal of 0 is undefined, creating an asymptote, and the reciprocal of undefined is 0. So the last thing I just want to talk about really quick is I want to talk about why haven't we been seeing horizontal reflections when we're graphing sine, cosine, and tangent. Now, it's not that they don't exist, it's just that the effect that they have on our graph can actually be treated in a different way than an actual reflection. So here's a quick review of the definition of even and odd functions. So by definition, if you have a function that is even, f of negative x equals f of x. So that essentially means that it is reflected over your y-axis. So it's saying if you have an opposite x value, so maybe the negative version of the x value, you get the same y value. So a positive x and a negative x give you the same y value. So you can see that our graph of cosine is actually an even function. So cosine is even. Again, even functions are reflected over the y-axis. And then here's a review of the definition of an odd function. So for an odd function, f of negative x equals negative f of x, meaning if you plug in an opposite x value, so the negative x value, you get the negative y value. So if you have like +1, +1, if you plug in the -1, it would give you a negative y value answer. So something like this, an odd function, another way to look at it graphically is that it's reflected about the origin. So actually our sine function is an odd function. So because we know that cosine is even and sine is odd, anytime you see f of negative x, which would be that horizontal reflection, it actually doesn't do anything to our graph. So we could actually kind of say, well, since it is even, f of negative x equals f of x. So again, a horizontal reflection doesn't actually affect our cosine graph. And then for our sine graph, which again is an odd function, if you ever have that horizontal reflection, if you ever saw it, we could actually just put a negative out front because it would have the same effect on our graph. So remember, a negative x value gives us a negative y value. So again, that's why we don't typically see them in the actual equation, but if you ever did see them, you could just either treat the negative like it doesn't exist because the function is even, or pull it out front and treat it more like a vertical reflection because our sine graph is odd. Now, if you look at tangent, we can see that same thing as sine. We see that tangent is an odd function. So it actually means that f of negative x, so a horizontal reflection is the same as a vertical reflection for tangent. So again, if you ever see a negative inside, we can actually pull the negative out front. And again, if you look here, just to prove that it is odd, here we have this point pi over 4, 1. And then you see here when we have the negative x version, so when we have negative pi over 4, the result is negative 1. So negative x gives us negative y, which is the definition of odd. So again, there's just a little bonus tidbit of how do you address a horizontal reflection, which we haven't really seen in our functions, and here's why we don't really see it. All right, so that is all for today's video. Thank you so much for watching.